welcome to day 2 of NTU Blockchain Symposium 2024. I hope everyone is well caffeinated today. We'll start today with session 5 on cryptography and privacy, chaired by Professor Feda Zhu. Professor Zhu is an associate dean and associate professor at the School of Computing and Information Systems at SMU. Please welcome Professor Zhu.
Good morning, everyone, and welcome to NTU. So I'm very happy to chair this session on cryptography and privacy. So I'm Feda Zhu from Singapore Management University, and I've been working closely with Prof. Wen Yonggang for many years on this domain. So I'm very happy to welcome everyone here. This morning, the first session, we have a very exciting group of professors presenting very interesting results. First talk will be given by Professor Joseph Liu from Monash University, Australia. Professor Liu is a full professor in the Faculty of Information Technology at Monash University. He currently leads the Monash Cybersecurity Discipline Group and the Monash Blockchain Technology Center. Having secured over $10 million in research funding, his awards include ICT Research of the Year 2018, the IEEE Technical Achievements Award 2021. And he is a very, very established researcher in this domain and published more than 200 papers in top venues like Crypto and ACM CCS. He's going to present a talk on quantum-safe cryptography for blockchain. Let's welcome Professor Joseph Liu.
Okay, good morning, everyone. So, welcome to the talk of me. And in fact, for me, my main research is on the cryptography and, of course, in the cryptography part of the blockchain. And therefore, today, I'm also going to give you a brief, some kind of presentation about the quantum-safe cryptography and blockchain. In fact, many people, when they heard about cryptography, they're a little bit afraid because, well, they may think that cryptography is some kind of mathematics, very difficult to understand, or, and they can simply ask the question why we need to know and learn these mathematics for blockchain or even cybersecurity. So today, I understand that these are the worries and concerns of most of the people. So in my talk, I promise you, I just give you kind of the concept-like presentation. There's no deep mathematics, so I hope all of you can understand and enjoy my talk. So first of all, just some brief introduction about my university. So Monash University is one of the top universities in Australia. We have established in 1958, and currently we have several campuses in different parts of the world, including Australia, Malaysia, China, and also Indonesia and Italy as well. And in the ranking, currently we are ranked one of the top 50 universities in the world. For example, the current ranking, the QS ranking, we ranked 37. And also in terms of the subject ranking, in terms of computer science, we ranked number 1 in Australia. And the faculty, I belong to the Faculty of Information Technology, so I'm more on the technical side of it. And in our faculty, we have more than 200 academics. It's a quite large faculty in Australia. And for our cybersecurity group, we also have 13 academics, and actually we are going to recruit more. And so if you have interest to apply for us, so feel free to go to our website, and the opening is still valid. And these are the focuses of our group, and mainly about cryptography. And because in the past, when I joined Monash 10 years ago, only 2 people, and I and other academics. So we are only cryptography, and therefore we grow along this core area, in particular the cryptography. So in terms of the blockchain research, we also mainly focus on the cryptography part, the blockchain. Okay, and I'm also the director of the Monash Blockchain Technology Center. In this center, we target to use our research to provide some solutions to different sectors, including, for example, supply chain, or the energy, or even the agriculture, digital agriculture sector as well. And today, let's come back to today, we are going to talk about how the quantum computer will play the role or impact the blockchain. Now, first of all, what is quantum computer? You may have heard about the word quantum or quantum computer, but what is it? Well, quantum computer, you can simply think of this is a very powerful computer. Different from the current one, your notebook, desktop, or even a mainframe computer, a quantum computer is able to perform some tasks that are not possible to be done in the current computer. So you can just imagine this is a very, very powerful computer. And the impact, what will be the impact of the quantum computer? If you heard about the quantum computer this word, you may also heard about, well, there are lots of things that the quantum computer can do, for example, do more computation, the AI things. But how about in the security side? In the security side, the impact of the quantum computer is, well, there are many schemes that are currently secure. For example, the very famous RSA encryption, the RSA signature. Well, these are the secure algorithm. Currently, it's secure. But how about the quantum computer? When one day, for example, 10 years, 20 years later, when a quantum computer becomes practical, now these are many current secure cryptography schemes, such as the RSA scheme, they are no longer secure because the quantum computer can be used to break this kind of cryptography schemes very easily. So one of these hard problem, what is a hard problem? Well, for example, the RSA scheme is based, the security is based on some mathematical hard problem. So this is one of the examples of the hard problem called factorization. I think all of you know what is factorization. Say, this is a primary school mathematics lesson. What is a factorization? So, for example, if I ask you what are the factors of 21, I think everyone knows what are the factors of 21. Even I ask my 7-year-old son, he may know that what is the factors of 21. 91 is also very easy. You can easily find out the factors of 91 without even looking into your smartphone or computer, very easily. So what is the hardness of factorization? It seems very easy. Well, that is easy because the number is small. How about this one? What are the factors of 603187919? If you are able to find it out without asking or without using your smartphone, I think you are the mathematician expert. But even if you use a computer, it seems not very difficult. Well, this large number is equal to 27529 times 21911. You can easily use some program or maybe some online calculator to find it out. So why is it difficult? Because when the number is going larger and larger, so how large is it, or how large, then we will say this is difficult. For example, if the number is 2048 bits long, when an integer is, how long is it? 2000 bits long. If we ask you to factorize an integer which is 2000 bits long, that is difficult. The difficult means even if you have the most powerful computer in the world nowadays, you can't find it out, you can't factorize the integer easily or efficiently. Efficiently means maybe you need 10 years or 20 years time continue to run the computer to factorize an integer for 2000 bits long. So this is difficult, and therefore we call it factorization is a hard problem, it's a mathematical hard problem. In fact, this hard problem gives the foundation of many cryptography schemes, such as the RSA scheme. The RSA scheme, the security is based on the hardness of this hard problem, the factorization problem. So, just give you a very brief example of what is a mathematical hard problem. We are not talking about, say, asking you to factorize 100 or 200, but we call it security parameter, at least 2,000 bits. If it is 2,000 bits long, the integer, well, this is a hard problem. So RSA relies on the hardness of factorization. So what does that mean? That means if you are able to factorize a 2,000 bits long integer, then you are able to break the RSA scheme. But because under the current technology, no computer can easily factorize a 2,000 bit long integer, and therefore the RSA is secure today, because no computer is able to factorize an integer easily. But how about in one day, for example, one day in the future, if someone, they can use a particular device to factorize a 2,000 bit long integer very easily, for example, in seconds, then what's happened to RSA? RSA is no longer secure. If someone can invent a machine that can solve this factorization problem easily. So in that day, RSA is no longer secure. So what will be the impact of that? A quantum computer. A quantum computer, just mentioned that it is a very, very powerful computer. And how powerful is it? Well, the current computer is not able to solve the factorization problem easily. But the quantum computer is able to do it. A quantum computer is able to factorize or solve for this mathematical hard problem in seconds. That means if I have a quantum computer, then I can use a quantum computer to break any RSA schemes very easily. In other words, RSA is no longer secure if any quantum computer becomes practical. Well, this is a quite serious threat to not just the blockchain, but to the general cybersecurity community. Because currently, many people, many schemes, they are still relying on RSA. When you look at your certificate in your browser, you can easily look at lots of certificates using your browsers. Many certificates, they are still using RSA scheme. So when quantum computer becomes practical, all these certificates, all these encryptions will be broken very easily. So this creates a very serious threat to the cybersecurity community. Okay, then you may ask, well, okay, RSA is no longer secure in the quantum computer, but how about other blockchain algorithms? It seems not many blockchain systems are relying on RSA. Will they be affected? Well, the most famous scheme that you may have heard of is the ECDSA. Well, this is the signature scheme that is used in Bitcoin and Ethereum and many other blockchain systems. So the first question is, well, will this signature scheme, will this ECDSA or the Bitcoin or Ethereum still secure when a quantum computer becomes practical? Well, first of all, we have to know that these signature schemes that are used in Bitcoin or Ethereum, the ECDSA, they relied on a mathematical hard problem called the ECDLP, elliptic curve discrete lot problem. So you don't need to know what it is. I'm not going to tell you what this hard problem is because it's quite complicated, but just want to let you know that, well, this hard problem, the ECDLP, can be solved by quantum computer very easily. That means, similar to RSA, once the quantum computer becomes practical, this ECDLP can be solved in seconds. In other words, the ECDSA scheme will be broken. If the ECDSA scheme is broken, Bitcoin or Ethereum or all these blockchain system relying on ECDSA will be broken. So that means you should be able to, if you have a quantum computer, you can easily forge a Bitcoin, you can easily make your own Ethereum or create many Bitcoins. That means the system will be totally broken because it can be easily done by the quantum computer to forge some of the Bitcoin or the other cryptocurrency that relies on the ECDSA. Now, of course, that is not a consequence that we want to see. Well, many people talk about the quantum computer, talk about the positive things of quantum computer. It can help the AI, it can help the health, bioinformatics. But actually, there's also some impact on security and blockchain as well. It's not so positive, but this is the fact that we have to know. That is, once the quantum computer becomes practical, the Bitcoin, the Ethereum system will be broken, because it can easily solve the problem, solve the maths hard problem, and of course break the ECDSA, in fact, break the entire blockchain system. So, what should we do? Well, we may not know how many years the quantum computers become practical, maybe 5, maybe 10, maybe 20, but we have to be prepared for that. Because once suddenly, maybe some company, IBM or Sony or maybe Microsoft or maybe Google, suddenly they announce that, well, we have already successfully to create a practical quantum computer. Then all these systems will be broken in seconds. So we have to do a preparation in advance of these quantum computers becoming practical. What should we do? One of the easiest thing is, well, we just need to replace the underlying ECDSA signature by another signature, which is a post-quantum secure signature. Post-quantum secure signature means, well, even if we have a very practical quantum computer, the signature is still secure, even if the quantum computer is here. So there are lots of this kind of post-quantum signature. For example, the lattice-based type of mathematical signature, which is secure against any quantum computer. So in fact, well, it seems we can just easily replace the underlying the ECDSA by some post-quantum secure signature, such as any lattice-based signature. Is it done? Just one reminder, the hash function is not affected. So you may know that, well, all the blockchain system, they relied on the hash function to create the chain. But the hash function is still secure when a quantum computer is practical. So the hash function is not affected. For example, the proof of work relied on the hash function. The hash function is not affected. That means all the consensus, the proof of work may not be affected, but the underlying signature will be affected. So is it done if you just replace the existing signature by some post-quantum secure signature? Well, this is not a difficult task, I would say. In the cryptography community, we started the research of creating all these post-quantum signature backdated to, I think, more than 15 or 20 years ago. So we have lots of different signature schemes that we can choose from in the post-quantum context. So it is not a difficult task. So that means, is it very easy just to replace it and done? Then we can say the blockchain, all the blockchain systems will be secure in the case, even if we have a quantum computer. Well, of course, not. It's not as easy as you think. So why it is not? Even if we replace the signature by a lattice-based signature, what is still needed? So before making it more clear, more transparent, so we need to first understand what are the type of cryptography that has been deployed in blockchain system. Of course, the Bitcoin or maybe Ethereum may be easier because, well, there's actually no privacy in Bitcoin. That means it's a public blockchain system. Everyone knows, say, the transaction amount or even the sender address, the receiver address. So it is not anomalous. It's just used a kind of pseudonym to hide your real identity. But in fact, currently, when all the on exchange, you need to do your registration using your own, using your real identity. So there's no privacy, and this is also one of the main concerns of being deployed in the real-world system, because many applications, they require some certain level of privacy, either the regulation requirement or the real requirement, the user requirement. So privacy is a quite challenging thing in blockchain system. How to protect the data and user privacy while having the advantages of blockchain. So how can we do that? How can we enhance the privacy of blockchain? We need to rely on some cryptography scheme. Unfortunately, encryption doesn't work. Well, encryption is the most common cryptography algorithm that can be used or can understood by everyone. You encrypt it, and of course, if you don't have the decryption key, you can't see what is being encrypted. It seems it's a very good way to protect data privacy or user privacy. But unfortunately, encryption may not work in the case in blockchain. Well, encryption may work to protect your wallet. That means if you don't want to, for example, being stolen by a hacker for your wallet, you have 5 Bitcoins in your wallet, you don't want to be stolen by hackers. Okay, you can encrypt it, store in the wallet, that is okay, that is fine. But encryption, well, unfortunately, it doesn't help to let other people know how rich you are. That means, well, you can encrypt it. You can prevent the hackers to steal your Bitcoin. But you cannot prevent other people know how rich you are. For example, you have 100 Bitcoins in your wallet. Because if you want to use your Bitcoin in your wallet, you have to, first of all, to decrypt it, and then to use it to send it to other people. In that case, other people, they still know, say, how many Bitcoins you have in this wallet, or what is the amount of this transaction. Is it 1 Bitcoin, 2 Bitcoins, or 3 Bitcoins? So encryption doesn't help to prevent other people know how rich you are. That means, well, you still need to decrypt it before you use it. So what should we do? Well, we have another type of the primitive called ring signature. So what is a ring signature? Ring signature is a kind of anonymous signature that allows other people to know, well, this signer is one of the people in this group, for example, in this theater, but no one knows who the actual signer is. So it's a kind of anonymous signature that can protect the user privacy. Well, this is a very, very good tool to be used in the blockchain privacy system, and Monero, well, one of the very famous the privacy-preserving blockchain, they use ring signature. But in fact, it's not the original ring signature, because the original signature cannot detect a kind of double spending. So 2 ring signatures, we don't know whether they are generated by the same people or maybe different people. So how can we ensure this double spending detection? So we have to use a kind of enhancement called the linkable ring signature. In fact, this is my PhD thesis, back date to 20 years ago in 2004. Of course, at that time, there's no blockchain, but this is my PhD thesis. I just want to graduate, and of course, I didn't patent it, so everyone can use it. And 10 years later, in 2014, Monero, they just used my PhD thesis, and in their white paper, you can see it, to put it into the system called RingCT to protect the user privacy. Well, of course, I didn't know that. So I didn't even get any acknowledgement, and I found it out later, I think in 2016. So I don't have any Monero at all. Otherwise, I would be a very rich guy. But this is a very, very good example to show that, well, cryptography can be used to protect the user privacy. And in fact, one of my proposed scheme in the past, linkable ring signature, has been deployed in the Monero nowadays. And but the interesting thing is, well, they make use of my 20 years of publication, and later, of course, I have made some improvement. And therefore, in 2017, I published another paper with a kind of improvement. And just upon to put it into the open public area, the price of Monero increased by 100% in a day. And the report saying that, well, this is because, well, someone in the Monero lab, they create a more efficient algorithm, but in fact, it is not true. I'm not the part of Monero. Again, I'm just a normal academics, just want to publish this paper in a famous conference stories, but just, well, this triggered the price of Monero to increase by 100%. That is equivalent to, I think, 500 millions in a day. I think this is the most valuable paper that I have published. But how about the quantum? Okay, well, all these papers, in the past, my PhD thesis and also the paper that triggered 100% of the price increase on the Monero, they are not secure in the quantum computer. So that's why after that, well, we started to do some research to migrate or transit the current, the ring signature or even the Monero, the protocol into a quantum-safe, privacy-preserving protocol. So these are the different papers that we have published. So the first one we published in 2018 is just a very, very naive one. So there's no very, very inefficient. And also in terms of functionality, there's no change can given. You have to send, for example, 1 Monero, 2 Monero. There's no single digit or division for that. And of course, we have done a lot of improvement from the first one to the last one. The last one is quite impressive. The IEEE SMP 2022, quite efficient. I think just 3 to 5 times longer than the current version. So it's quite efficient right now for the recent quantum-safe, privacy-preserving protocol. Okay. Well, another, in addition to the privacy, another the more advanced is called the VRF, the verifiable random function. It is usable in the proof-of-stake protocol. So you know the proof-of-work is quite old and then it's not efficient, it's not energy efficient, but proof-of-stake is a more modern consensus protocol. But it relies on one of the mathematical function called the VRF, verifiable random function, to verify that. So you generate a random number according to the algorithm, but not just think of a real random number, but you have to every miners, they generate a number according to the algorithm. So that's called a verifiable random function. And the current one, for example, the current one deployed in Algorand is a VRF. It's based on RSA, so that means it's not quantum safe. And in 2022, we also invent quantum safe VRF, which is quite interesting. It relies on just hash function. It just relies on a bunch of hash functions. As I mentioned before, hash function is secure in a quantum computer. So if our VRF relies only on some hash function, it is secure even if there's a quantum computer. So by replacing this VRF into the existing one, so we can have a quantum safe, maybe proof of stake protocol as well. And the last primitive that I just want to talk about today is called the multi-signature. So multi-signature, that means for multiple people, they sign on the same message. But this is very useful, in particular in the digital wallet. In the e-wallet, if you want to have a more secure wallet, for example, you require yourself and your manager, maybe also the director, to sign on the same amount, so that, well, even if, for example, your private key is stolen, it's still secure because it still requires your manager and director to sign in order to spend a Bitcoin. So this is quite secure setting in the current Bitcoin or the digital wallet. But in the multi-signature, of course, they are not quantum secure currently. So therefore, we invent another new one, also using some kinds of hash function this year in crypto that has been just published last month to provide a kind of quantum safe environment so that you can have a quantum safe digital wallet, an e-wallet in the future. Because of the time being, I'm not going to give you the details of these under this mathematical function, but in fact, if you have interest, just let you know that this new primitive, different from the lattice space, it is based on an interesting mathematical function. Yeah, this is called a Lagrange symbol. So this is one of the first topics that I learned when I learned the number theory in my undergraduate studies. Lagrange symbol, well, in fact, it is very easy to solve for the problem, for the Lagrange symbol, Lagrange PRF. But what we relied on is the keyed Lagrange PRF. That means if you don't know the key, if you don't know, for example, the secret key, you cannot derive the public key, or you cannot sign a signature without the knowledge of any secret key. In this setting, well, this is actually secure even there's a quantum computer. So by having this as a primitive, so we can easily derive the quantum safe multi-signature. In fact, I just want to show you some of the computation between our proposed scheme, that the latest one, with all the previous scheme. Well, all the previous schemes, they are also post-quantum secure. But when we try to do the multi-signature, that means if you want to have a kind of secure wallet, our signature will be the most efficient one. But we look at the middle column, the R1CS. This is kind of the figure that we need to look at when we try to aggregate or compress different signatures. The smallest, the more efficient the index for this kind of multi-signature. So when we talk about the multi-signature, of course, we choose the smallest number, which is our scheme, which is the state of the art, the most efficient multi-signature scheme, which is also quantum safe in the future. So this is just the performance of our signature. We can easily compress 64 signatures within this certain amount of the computation resources, while the other schemes, you can see even the Sphinx, which is the only one scheme based on hash function to be included in the NIST standardization of the quantum safe. They can just compress up to 18, but we can compress up to 64 signatures with the same size, the same under the same computation resources. So I think, yeah, for the time being, just want to show you this is the work that we have done for the cryptography in blockchain. So as a cryptographer, of course, we try to use different cryptography to improve the security and privacy of blockchain, and this is part of our work in this area. I think that's all for my talk, and looking forward to working with you all. Thank you.
Okay. Thanks, producer, for the nice talk. Any questions from the audience? Yes.
Thank you for your presentation. I'm not an expert in the field, but what's the process of migrating to new signature schemes on a blockchain? Because you can change the past, but can you upgrade the signature scheme from time to time for the newer records in the blockchain, or do you have to completely set up a fresh blockchain?
A very good question. In fact, it's not an easy task to change the signature scheme. Of course, you can create a hard fork, but you have to also get the consensus from the community. In fact, this has been done in Monero in the past. Not the signature scheme, but in the past, they used a kind of schemes to somehow to compress it, but later on, they use the most efficient so-called compression algorithm. So they need to go through a hard fork, and of course, there are lots of debating or consensus in the community. But once they got a consensus, and once create a hard fork, the schemes can be changed.
Thanks.
Any other questions? So I have a question. So when you hear people talking about these post-quantum solutions, sometimes people argue that it is very hard to balance the need for efficiency with integrating these solutions. So how do you? What's your take on balancing the efficiency and the solution? Yeah.
This is also a good question. So if you do not need to concern efficiency, that is easy. But when you need to make a balance between efficiency and security, that is the most challenging task as cryptography researchers. As you can see previously in my in the list of the different signature scheme. The first post-quantum, we call it ring CD scheme, published in 2018, is 100 times larger than the current one. Of course, it's not acceptable. So we try to improve shorten 100 times, 50 times, 10 times. The most efficient one is, I think, 3 to 5 times longer than the current one. So, well, of course, you still have the trade-off. You can't, very, very difficult to make it as a one-to-one. But later, if we can think of it, if the security is more important, and we can also sacrifice some kind of efficiency, for example, maybe 3 times or 5 times longer, in that case, we would say that it's still a balance that you can make. But of course, at the same time, we would try to continue to improve the efficiency of this kind of post-quantum algorithm.
I see. Thank you. Thank you. Any other questions? Let's thank Joseph again for the interesting talk. Thank you. I wish I can hear the talk maybe 10 years ago. So